Hello, everyone. I'm Shraddha, and I'm a postdoc here at UMD. I did my PhD from University of Cincinnati, my master's as well from there. And my main research is on cooperative transport, swarm robotics, but multi-drone cooperative transport. And today I'll be talking about how to balance a ball on two drones using reinforcement learning. So this is the state of the art on cooperative transport. And you can see there are different types of control schemes used: geometric control, admittance, adaptive, sliding mode control, vision-based control. And all these control techniques have been tested for different types of connections, such as for cables, for rigid connections. Cables, strings are there. Rigid connections means that the drones are rigidly connected to the payload. Flexible connections like spherical joints, and different types of uncertainties have also been addressed, such as what if the mass of the payload changes, what if the center of gravity changes, and the types of robots. Here I'm talking about drones, but all these schemes have also been tested for ground robots. And in this work, specifically in this work, what we are trying to do is that we are trying to balance a ball on two drones. So this means that the center of gravity is continuously moving. In all the work till now, the center of gravity was assumed to be fixed or known to be at the centroid of the geometric center of the payload. But here, we don't know where the CG is. We don't know the velocity of CG. And we are doing this with rigid connections. It's very challenging to do it with rigid connections because we know a drone, when it tilts, it starts moving in that direction. So when we have rigid connections with multiple drones and the whole system, if the whole system tilts, it will start moving in that direction. And plus, balancing a ball on top of that is another headache. So all these form the challenges which I'm trying to solve in this work. So these are just some motivating ideas I got. So we have a ball on a plate robotic system. Everyone knows about that. And the main thing here is that the controller is centralized. If you check all the papers on Scholar, this controller is centralized. How to use decentral control for balancing a ball on a plate? So forget about ground robots. We are trying to do it on drones. And then there is one more futuristic idea. Like if we just lift a table and we all decide that the ball should not fall down, how can we win that game? So that is another. I don't know what happened. Give me a minute. So these are some motivating ideas. I'll go on the next slide. But if you saw on the current slide, that two ideas were there: ball on plate and humans transporting a table with moving balls. So I'll just go on the next slide, on this slide. And there is package delivery as well as a flying taxi application. So in the flying taxi application, what if people start moving inside the flying car? That will change the center of gravity. So you have a multi-drone flying car with many people inside the flying car. And when people start moving, the CG is going to change. So how each drone is going to come to know where the CG is and how is it going to control or mimic the leader or cooperate with the leader. So in this, the problem is posed here. So the leader is shown in blue color and then the followers are green. So how do you mimic the leader or how do you cooperate with the leader? How should you train or how should you develop the control strategy for the followers to mimic or to cooperate with the leader such that you use little information about the leader? Now, why you have to use little information about the leader? Because the center of gravity is moving. In all the work studied so far, wherever there is uncertainty in the payload, you have to know certain information, like where the followers are trying to go or what is the information of the leader. So that's why you have to exchange little bit information about the leader to control or to stabilize the system. So this is the system dynamics. We start with the world frame, then we go on to the body frame of the object and the body frame of each drone. And then we simulate the contact forces at the point of contact between the drone and the payload. Each drone exerts four forces. There are four thrusting forces of the drone, and the net force is shown by capital F and small tau. And then once you have all these forces acting on the payload due to the drones and due to the weight, you can write down the equations of motion of leader drone and similarly for the follower drone. And then the equations of motion of the object, the entire object, how many forces are there on the object, the weight of the object, the CG forces. And then you have the rigid body equation to compute the final uh, acceleration of the CG. Now check in the last equation, you have RG dot and RG double dot. In all the work, they said that RG is fixed. So RG dot was ignored. RG dot was taken to be 0. When this work, we are considering RG dot as well in this work, and RG double dot is assumed to be 0. So we can estimate, we can control the system because we know the CG is moving as well as it has a velocity component as well as it has a position component. So leader, in my work, leader can be any controller. It can be a sliding mode controller. It can be, but it has to be perfect in balancing the CG. But the follower, here I'm using reinforcement learning and I'm using soft actor critique. So I chose soft actor critique for followers reinforcement learning. That's because soft actor critic gives a good trade-off between exploration and exploitation. Since the CG is moving, you get some uncertain data and you get some good motion for the RL agent to learn quickly. So that's why I thought that maybe SACO will be a good choice, although I've not tested the other architectures yet, but I will test them in future. So three networks were deployed, actor, critique, and value, and soft Bellman residual and Kullback-Leibler divergence equation were utilized. And the parameters are indicated later in the slide. So this is the main follower control. Now, what the follower is trying to do is, it doesn't know where the CG is. It doesn't know, it knows little bit about the leader. So the state of the follower drone is its own local information and position of the leader. You have to share some information to stabilize the system because the CG is continuously moving. And the action for the follower is the action used for the drone to get activated. And the reward is simple. The reward function is formulated in such a manner that so the follower is going to try to mimic the leader. So the leader is perfect and the CG is moving. So if you can mimic the leader properly, the CG will automatically get balanced. If the leader is perfect in stabilizing the system, all you have to do is mimic the leader. So the reward function is formulated in such a manner that PZL is the control action of the leader and PZF is the control action of the follower. And you take the error between the two, and that gives you the reward function. These are the results which I got. I think I'm too fast. So these are the parameters I used. Learning rate was chosen as 0.0003 and discount factor of 0.99. And two-layer neural networks with 256 neurons in each layer were used. And this is my performance of SAC implemented on the follower drone. One more point I wanted to mention is that I'm using PID control for the leader and RL for the follower. I could have said, let's use RL for both the robots. But I didn't do that because we know that machine learning algorithms and AI-based schemes, they are data intensive and they are dynamics free, but they're data intensive. If the data is wrong, they'll not behave properly. There are no stability guarantees. But for the traditional control approaches, they are perfect, but they are heavily dynamics dependent. So to get a good trade-off and to get a good hybrid between the two, I chose one robot to be leader and to be PID and other to be RL. And good thing about this is tomorrow we don't want all robots to be replaced by AI-based robots. In industry, there are currently many robots running traditional control approaches. So we'll rather want to introduce some minimal robots first and see how they're interacting with traditional robots, and then see how to expand from there. So these are the results. I tested this architecture and I compared it with an adaptive control scheme. Green is adaptive control and blue is the RL based. And as you can see from the plot, the settling time for our proposed method is better, and adaptive control is not that good. You can see some oscillations in Z direction. That's because adaptive controller will first estimate where the CG is, and then it will give that estimated CG to the controller to control the system. So this is the reason adaptive controller is little slow, and you see till the point it learns, it shows some oscillations. But RL part, this framework gives you better results. And on the left here, you can see that this system was tested for different CG speeds. So this whole system was tested for a slow moving CG and a constant fixed mass. But I said, let's change the mass of the payload. So what if we add more mass on the payload? What if we drop the mass? What if we increase the speed of the CG? Will it still be stable? And this plot, these two results indicate the effectiveness of the proposed scheme, that even if you change the speed of the CG, even if you add or drop mass of the payload, whatever happens, uh, you know, uh, let the inertia be unknown, let the mass be unknown, let the CG be unknown. I'm yet to test the inertia part. But payload uncertainties can be handled well. And one intuition about this is that when the uncertainty in the payload is there, it will give more data to the RL agent to train. Like you cannot just give one point continuously and ask the RL to learn from magic. You need to give it diverse data. So uncertainty kind of gives it a diverse range of data for it to learn well. This is my intuition. But it can be seen from the results as well that even if you increase the CG speed and you change the mass, the results are more stable and they are not affected. So I tested this on a test stand, and I know they are drones, they are not supposed to be on a test stand, but to just test my scheme in my simulation framework, I had used the same geometric parameters which I have used in experiments. And L is the leader, F is the follower, and the circle, yellow circle is the ball inserted on the slot, and both the drones are supposed to balance the ball. So the arrow indicates the direction of the motion of the ball, and I'll just show a video. So this is the simulation of the entire scheme. The red is the moving CG, and blue is the RL follower, and green is the PID leader. And in simulation, I noticed that the system was very slow. So I was a little skeptical that in experiments whether it will work properly or not. But in experiments also, it gives good results. So you see RL follower is here, and PID leader is on the left, and the ball is being able to balance. So good thing about this is that the balancing thing was going well. But as I indicated before, if the drone tilts, it will start moving. So because of the ball, when the whole system is going to tilt, it will start oscillating. And we won't know whether the ball is getting balanced or whether the system is reaching the waypoint or not. So I tested this in actual flight, and the ball is getting balanced. As you can see the oscillatory motion, though I'm flying it at a lower height just to see the ball, and I'm still working on the tuning aspects. This flies little higher. The ball remains at the center, is trying to remain at the center. So I'd like to say a few comments before I wrap up. First of all is that you had to exchange some leader information to the RL agent. So next steps are going to be that I want to remove that information, though adaptive strategy, sliding mode, all use some leader information. I want to completely eliminate that and see if it still works. Then I'm going to try using all RL agents. I'm going to try using testing it for inverted pendulum as well. And these are the next steps. I'd like to thank Maryland Robotics Center, Dr. Chopra and Dr. Paley, my lab mates, and Ivan for their help. And these are some relevant references. And I'd like to invite any questions.